Today, I'm not talking about voters. Voter Ralph is going to talk about voters. But I'm talking about my previous research back at Illinois. Here, I will try to focus on one particular technology that I bring them from basic research to about final products, and in 10 years. So it's not a very short period of time. As you can see here, my history is, I think I try to develop so many different kind of technology. This is the last one that I'm doing the voters. But very early time, as you can see, there is a need. The society there has a need for infrastructure monitoring. And what is lacking is not only the system integration is the most important, but some of the missing link. Some of the sensors may not good enough, or some of the sensors may not convenient or even cheaper enough. So at that time, I'm starting to talking about wireless, strength sensor, wireless network, and also the system integration for a bridge system in terms of all different kind of sensory array. And so from there, from that end, from the last 10 to even 20 more years experience, I feel it is hard to bring up a new technology to the market. And now, if you're only using the existing technology, even that you have a hard time, okay? Because your end user, which is the stakeholder, may not want whatever you try to provide. And so we have to communicate between the provider and also the end user. And end user part is very important, as you are going to see through our panel's discussion. We already know we have lots of story and also example about bridge collapse. And the bridge collapse could be sometimes because of the error due to construction, error due to the design, and also the error during the construction. And somehow we also have a failure which is triggered by large event like an earthquake or like a scouring of a flood, and also some impacts due to the security reasoning. So we have a lot of examples about all this, and then a lot of them are related to a long-term deterioration. And so what I'm talking about health monitoring is talking about how can we predict the long-term health. And so that long-term meaning maintenance. So the maintenance related to long-term monitoring, that you have to bridge them, that bridge the gap. And so if we know this in advance, then we prevent this from fail or from killing people. And if we know how to maintain our structures, I think we're saving the money for a long run. And so let me describe about what I mean by structural health monitoring. It's the integration of sensing and possibly also the actuating device to allow loading. I'm talking about loading. A lot of time we do not know exactly loading. And the abnormal condition, I don't say damage, because a lot of time it's only abnormal. It may not cause immediately it may not cause immediately failure of a structure to be recorded. So you have a lot of database. You analyze them from your civil engineering point of view or from other physics point of view. You have to localize where is the problem. Some of them are very localized, some of them are global. You cannot solve the global problem from a local one. So you have to balance between your localized solution with your globalized kind of prediction. And so eventually we hope we can predict, and most importantly, our life cycle measurement or our life cycle calculation. And hopefully we have a structural health monitoring to do the early warning detection. And that will be the two major ones. A lot of them you will see in the NDE, non-destructive testing. Now non-destructive testing is not like that, okay? It's just trying to solve a more localized problem. And I hope this will give you a well definition. So let me give you an example. If you talk to your vendor or you talk to your stakeholder, there must be a purpose for you to design a structural health monitoring system for them. And usually you can see this example like to verify as design condition, to verify loading condition, which is very important, to create the database for baseline, because you have a new structure, you need to have a baseline. If you measure after 20 years, you need to know their current resistance capacity, you need to determine their baseline. To detect abnormality after construction, I'm not using damage most of the time anymore. To monitor extreme events such as typhoon, earthquake, and also the impact. To monitor overweight traffic flow, which is very important for some country. A lot of our highway has been over flooded with heavy truck and so on. You have to monitor them. You have to know when they happen, how much the weight of those traffic to provide database for maintenance priority. And that's what we do for voters, and that's what we do for a health monitoring system. If you can provide a very good database for the maintenance purpose, then you have a value. You have an added value, not for the sake of the monitoring. Give me an example. This is Zhanjiang Bay Bridge, which is constructed by my colleague, Dr. Cao. And he constructed this bridge, and I'm working with him to develop a health monitoring for him. And we two both agree we want to create a simple system, but useful enough to check the above example condition. I mean the objective. And so we try to maintain the cheap or the economical measure, and to provide the most up-to-date type of sensor technology. And so this is one of the example. In this bridge, as you can see, is a large cable stay bridge, and we have a sensor inside the bridge deck. We have a, we have a GPS and some other sensor. So go to next example. You can see this is the sensor we select. And today I'm going to focus on this because that's what I developed. And this is what I bring them into the market. And I want to show you, along with some other sensor system, that how do you integrate them, another system that we developed to integrate them, and so that it can become a good solution for the customer. And so, in particularly today, I will focus, because we're talking about from research to reality. And this is part of our research, and this is right now the product on the market. And this is we call cable force measurement by electromagnetic technology. And so that's called EM sensor. So I'm transforming right now my talk from the health monitoring to the sensor technology. We know there are so many different sensor systems that you can use, but today I'm just more focused on this one because that's from my life story. All right. And along the way, you can see I also developed the PVDF wireless strength sensor. You see this, everything you start from fresh. This is the only raw material we bought, PVDF. We know how to cut them and devise them into a wireless strand and also temperature sensor as well. But it's not successful because they are not durable enough, okay, by the way. And this is a wireless MEM sensor, accelerometer. So along the research line, I'm starting to talking about if I wanted to go to wireless, I wanted to go to a better, more like, what I call, a laser sensor. They may not be so useful or only measure one item. But if I have many, I'll be able to solve a problem from that kind of perspective. So if we have a cheaper accelerometer and if they are wireless, you can distribute them everywhere and you can solve your problem that way. So at that time is my thinking. So this is one of the example. I'm not going to give you a lot, but for example, this is your force. This is your temperature you measure. And then this is a force using the sensor you measure from your cable. So this data is important because you want to know their up and down variations so that they won't be here, they will not be here. And from the temperature, you want to see whether they response to temperature or not response to temperature. And so on. And I want you to take a look at this. This is a result from this cable force and also the health monitoring system. And this is from the realistic data. As you can see over here, this is the sunshine come from here and then right now moving and coming back to in the midnight. Actually, your structure is realistically moving along the clock. He is alive because of your temperature movement. And from here, you can see whether there is abnormality or they are response to according to your calculation, according to your design. Basically, when the sunshine coming out, I'm sorry, how come you suddenly push so much? Sorry about that. So basically, when the sunshine is moving, the sun is moving, and so your power has exposed more sun from here, so it's hot, you get more heat. And then when you come in here, you are exposed to this side. So because of the side and the exposure of your tower and also your deck, then you have a different kind of response. And this is from the measurement. This is not simulation. This is from the data, and so on. And so therefore, you use this information to do a lot of characteristics. This is the same bridge, and you can see this is without loading. That's in the midnight, almost no traffic. This is wired during the heavy traffic. And this is what? During the typhoon. So you see this measurement you can see dramatically they changing the structures vibration as well as the displacement. However, the 9 is very similar, so it says the structural integrity kept very much intact at all. So that's another example I did in United States here over in Illinois. This is a box girder bridge. When I was first to ask over there to do the monitoring, I found out there are so many cracks. And again, we devised this system in a kind of a health monitoring system, and then we keep this health monitoring system for 5 years until they retrofit last year. So they have finished the retrofitting. And so with this kind of continuous monitoring, you will be able to find out their crack is very active. And that active crack increasing about 50 to 60 micron in the last 5 years of time. And 110, some of them are 110, some of them are much more. And so, therefore, the decision maker decided, I think we need to retrofit the bridge. Instead of destroy the bridge, one time they're talking about to rebuild the whole bridge. All right. So let me go back to talk about the EM stress sensor. The EM stress sensor here, from the National Science Foundation program to the final company developed or spin out, is about 10 years time. And the EM sensor is a long-destructive testing technology. We use that to measure the stress, not the strain, okay? The stress and then the corrosion or the force of the steel. All right, so it's an electromagnetic sensor that non-contact, and the magnetic sensor does not touch the specimen. Actually, it's just magnet to produce that. All right, so based on the property of permeability, which is meaning your excitation and your induction and the slope in between, that's called permeability, and your driving force, which is your primary force, and there is a certain linear relationship in between them. In the lower induction, in the lower induction force, then you have more very sensitivity very high, but it's not very linear. But in the very later on, you have very linear related to your stress and also to your stress to your permeability. And the sensor actually is you have a primary coil, and then you have a secondary coil, and then you have a protection mechanism over here. And coming up to the equation then is very simple. Your permeability is related to your stress, your temperature, and your introduction force, okay? Your primary force, magnetic force. And as you can see, there are so many different kind of cable. So we calibrate all these cable related to their different type. You can see gradually from the smaller and the very smaller and also larger size, they all fit into very linearity curve up to about 60% of your yielding stress. All right, so here I'm talking about this. From the very early development, you can see all different sensor size, and we even have to develop our own box and electronic. And so we don't have anything else to helping us except the voltmeter. And so from there, we had to develop all the electronic for many years. And eventually, you are smoothing out, and you have a very good sensor size being developed. Some of them are very small. This one used most frequent. And then we have a larger size for large cable. And this is the box that we use to generate the magnetic force and also the products. Okay? And actually, the sensor can manufacture in-house. And you can see here is mass production, okay? And also you can manufacture in the existing cable. It's very important application because most of them are in existing cable. And as you can see here, it's a mass production. So here, from here, you can also do the calibration, packaging before you ship to the site. So those kind of business that you need to think about when you develop a certain sensor. How are you going to do that in a kind of company setup, in a kind of application setup? And so that's another example of mass production of this sensor. Look quickly. I don't want it to be too specific. But we have to use this, we currently use this a lot in the kind of retaining wall or the stability